칼만 필터에 대한 개괄적인 첫 동영상을 시작하도록 하겠습니다. For statics and control theory, Kalman filtering, also known as linear quadratic estimation, that is LQE, is an algorithm that uses a series of measurements observed over time, including statistical noise and other inaccuracies, and produces estimates of a known variable that tend to be more accurate than those based on a single measurement alone, by estimating joint probability distribution over the variables for each time frame. The algorithm of Kalman filter works by two-phase process. For the prediction phase, the Kalman filter produces estimates of current state variables along with their uncertainties. Once the outcome of the next measurement necessarily corrupted with some error, including random noise, is observed, these estimates are updated using weighted average, with more weight being given to estimate with greater certainty. The Kalman filter algorithm is recursive. It can operate in real time using only present input measurements and the state calculated previously and its uncertainty matrix. No additional past information is required. Optimality of the Kalman filtering assumes that the errors have a normal Gaussian distribution. Physical random phenomena may be thought of as due to primary random sources exciting dynamic systems. The primary sources are assumed to be independent Gaussian random process with zero mean. The dynamic system will be linear. Though regardless of Gaussianity, if the process and measurement covariance are known, the Kalman filter is the best possible linear estimator in the minimum mean square error sense. Kalman filter is based on linear dynamic systems described in the time domain. In order to use Kalman filter to estimate the internal state of the process given only a sequence of noisy observation, one must model the process in accordance with the following framework. This means specifying matrices for each time state k following Fk, the state transition model, Hk, observation model, Qk, the covariance of process noise, Rk, the covariance of observation noise, Bk, the control input model, Uk, the control factor representing the controlling input into control input model. The Kalman filter model assumes the true state or time k is evolved to the state of at k minus 1 according to like this, where Fk is a state transition model which is applied to previous state xk minus 1. Vk is a control input model which is applied to control factor Uk. Wk is a previous noise which is assumed to draw from zero mean multivariate normal distribution and with the covariance Qk like this. At time k, an observation or measurement Zk or true state at k is modeled according to like this, where Sk is the observation model which maps the true state space into the observed space, and the Vk is the observation noise which is assumed to be zero, mean Gaussian white noise with covariance Rk. The initial state and the noise vectors at each state are all assumed to be mutually independent. Many real-time dynamic systems do not exactly conform to this model. In fact, unmodeled dynamics can seriously degrade the filter performance even when it was supposed to work with unknown stochastic signals as inputs. The reason for this is that the effects of unmodeled dynamics depends on the input, therefore can bring the estimation algorithm to instability if it diverges. On the other hand, the independent white noise signals will not make an algorithm diverge. White noise in signal processing, white noise is a random signal having equal intensity at the different frequencies giving a constant power spectral density. In discrete time, white noise is a discrete signal whose samples are regarded as a sequence of serially uncorrelated random values with zero mean and a finite variance. The problem of distinguishing between measurement noise and unmodeled dynamics is different one and is treated as problem of control theory using robust control. The Kalman filter is a recursive estimator. This means that only estimated state from the previous time step and the current the measurements are needed to compute the estimate for the current step. The notation x and m represent the estimate x at the time n given observation up to the including at the time m not larger than n. The state of the filter is represented by two variables x, k, k. The posterior state estimate of time k given observation up to the including at the time k. P, k, k. The position estimate covariance matrix, a measure of the estimated accuracy of the state estimate. The Kalman filter can be written as two distinct phases, predict and update. The predict phase uses a state estimate from the previous time step to produce estimate of the state at the current time step. This predicted state estimate is also known as a priori state estimate because although it is an estimate of the state at the current time step, it does not include observation of information from the current step. In the updated phase, the innovation, the prefect residual, that is the difference between the current a priori prediction and the current observation information, is multiplied by the optimal Kalman filter gain, Kalman gain, and combined with the previous state estimate of the defined state estimate. This improved estimate based on the current observation is termed as posterior state estimate. Typically, the two phases alternate with the predictions advancing the state until the next scheduled observation and update incorporating the observation. However, this is not necessary if an observation is unavailable for some reason. The update may be skipped and multiple predictions performed. Likewise, if multiple independent observations are available at the same time, multiple update approaches may be performed, typically with different observation matrix HK. 자, 다음 이부터 이 내용은 두 번째 동영상에 담겠습니다. 일단 내용을 제가 정리한 걸 쭉 읽어봤는데 그냥 뭐 이해하시면 이해하시는 대로 편하게 받아들이시면 되겠습니다. 칼만 필터가 주로 프레딕트하고 업데이트 하면서 그 다음 우리가 계속 예측한 건데 우리가 항공기 제어할 때 보면은 그 현상을 빨리빨리 기존 거를 갖고 빨리 업데이트해서 다음 현상을 파악해야 비행기를 제어할 수 있겠죠. 그래서 비행기 쪽에서 많이 쓰는 칼만 필터를 칼만 필터로 해서 필터하는 것보다는 주로 에스티메이션 성격이 강한 겁니다. 차차 수학적인 거는 다음 동영상에서 좀 더 얘기를 하도록 하겠습니다. 감사합니다.